Welcome. This is our lesson over exercise 5, underfitting and overfitting. And in this lesson, we're going to learn how to adjust the decision tree regressor by limiting the number of leaves it can create. And by doing so, we can make it underfit, or we can make it overfit, or we can try to get right there at the best possible place. And we'll show you how to do that work today. Awesome. Just as a recap, we're going to import a bunch of libraries. So we import the entire Pandas library. Remember, the Pandas library allows us to do some data analysis and work with data. So that's helpful to have. And then we're going to bring in, instead of bringing the entire sklearn library, which is enormous, we're going to bring in just bits and pieces of it. So from the metric section, we're going to bring in the mean absolute error. And remember, this function is going to allow us to calculate how close our house values are to the actual values and give us one number that gives us the average amount that we're off by. We're going to also bring in the train test split function. And this is that function that takes all of our huge set of data of 1,400 houses and breaks them into a large training set and a smaller validation set so that we can train a model on one set of houses and then go back and validate it and test it on houses it hasn't seen yet. So that's really important to do. And then the final thing we're going to import is the model we're going to actually use, the decision tree regressor model. We're going to bring in that blank model right away. All right. Next thing we're going to do is we have to tell the computer where all of our data is at. So it's in these folders. And then we're going to read it using a Pandas library. We're going to read the CSV file, which is a convenient way to store data, into something that the machine learning can use, which is a data frame. And this read CSV function does that. It converts CSV into data frames. It's going to store all of that data as a data frame called home data. So now all the data about all 1,400 houses are in home data now. Okay, next thing I have here, I don't know if yours has these two, but if we were doing anything with this data, the first thing we want to do is print off the head, which will give us the first couple rows so we can see what kind of data is in the columns. It would also, we would also want to do so you can see this a little better. We want to do a columns as well. And then we might also actually do a print describe. I always forget, like head and describe both need open close parentheses. Columns does not. I always forget that. So if you get an error, if you put parentheses after columns, you'll know just delete them. But these are the three things we would need. The columns is going to tell us exactly what every column is called so that we can choose which ones we want. All right, so I'm going to go back and hashtag these. I don't know if I could do it. Yep, like that. And then next thing we do is tell the program what we're trying to predict. And in this case, we're trying to predict sale prices. So because we only want to grab one column from the home data frame, we can use the dot notation, which is the data frame, all of the data, and then dot sale price says, go find the column called sale price in the home data frame and put that into the variable called Y, or the list called Y. Now we have a long list of all the houses and the sale price of all the houses. All right, next thing we need to do is tell the computer what things that we're going to use to predict with. In this case, they're called features. We're going to use these features to do our predictions with. Now these names need to exactly match the names of the columns in the data frame home data. To actually pull them all out and put them in its own thing, we can't use the dot notation like this because it's more than one. So instead we do home data, square bracket, and we put the features list inside. So this says, go get all of the columns with these feature names and store them in a new data frame called X. All right, so we've got what we're trying to predict. We've got what we're going to predict with. Now we need to split those big data sets into validation and training data, and that's where the train test split is going to come in. So we call this function, we send into the function all of our X data and all of our Y data, and we set this random state feature, which all this does is, if we run this bubble 3 times, the random state of 1 will keep the split happening the exact same way every time. If we don't define a random state, every time you run this bubble, different houses will go in the validation and training data, changing our results a little bit, but it's not that big a deal, but we set it just in case. All right, the other thing that the train test split it's going to create 4 data sets, a training X, a validation X, a training Y, and a validation Y. So we need those 4 variables in this order here. In Python, you can make multiple variables just by putting a comma in between them, which is kind of cool. All right. Next thing we're going to do is we're going to actually go get the model and get it set up. I'm going to hit play real quick in this bubble just to get it running in the background. So we have the decision tree regressor model, and we're going to set its random state to 1 for the same reason up here. We want it to run consistently every time and not slightly differently every time. So we're going to go get a decision tree regressor and store it in this thing called Iowa model. Later we'll learn that you can actually set more properties, more parameters for this decision tree regressor to make it work better. Right now we're just setting the random state. Then we're going to fit the model. So we're going to do Iowa model. That's where our empty model is stored at. We're going to do fit, and we're going to fit it with the training X and the training Y data. This is where it goes through and makes all of its decisions, puts all the data in there, and puts all the values in there as well. Now that we have our model fully trained and ready to go, we need to make predictions with it. So we're going to go Iowa model.predict, and we're going to predict using the validation X data. Now these are houses the model has never seen before, so we'll be able to see how well it does with new data. And all those new predictions, so all those sale prices that it's predicting for all the validation X houses, will be stored in a list called val predictions. All right, now we need to see how close our predictions are to the actual stuff. To do that, we're going to use the mean absolute error function that we brought in from sklearn. We're going to say, okay, our val predictions, this is what our model predicted, all the values of the house. These are the actual values of those same houses in our validation data. It's going to subtract those 2 numbers up together. So it's going to subtract the 2 numbers and then takes the absolute value. And that will tell us how far off we are, not caring whether we're high or low. Then all of those differences, it's going to average them together to give us one number, which is on average, how far off is our model. It's going to store that one number in something called val MAE. So a variable we created called val MAE. Then it's going to print the words, because it's in quotation marks, validation MAE. Don't worry about all of this. This is like formatting stuff for this dot format thing. We won't use it in ours. And it's going to print validation MAE. So it's going to put that number there with some nice formatting with it. All right. And then this last little bubble of code here, this last little bit, this is just setting up the activity and the exercise to do all the check and the solutions and all that stuff that they're doing for the program. All right, I've already run this bubble, and we've gotten a validation MAE of 29,653. So that's how much, and I'm actually going to put a $sign right there and run this bubble again. Good. That just put a $sign right there. You can tell that. So we're off on average by $29,653. Setup complete is just letting us know that the notebook's ready to go. All right. So that was just a quick background. Next thing we're going to do is, I hate that they did this, but they did, so we're going to use it. They created a definition, or a function, I should say. And the way you create a function in Python is you use def. In JavaScript, we would use the function command, and then we would name our function and say what parameters it has. In this case, they name their function getMAE. So my guess is that this function is going to actually calculate the mean absolute error. And we need to send in some data into this function. So we need to send in what's the maximum number of leaf nodes that you want to use. So that's what's going to come in. The first thing in the parameter is going to be that. Then we need to send in our training X data, our validation X data, our training Y data, and our val Y data. So we send all those in. It's going to use them during the function. First thing it does during the function is it creates a decision tree regressor. So here we're actually setting 2 parameters. The random state 0. Like always, we're just starting with a random state. It's the same random state. But we're changing the max leaf nodes here. There's also a property called max leaf nodes that we can set in the decision tree regressor. And we're setting that to max leaf nodes. I wish they hadn't used the same name for this and this, but this one on the right-hand side is actually this first thing here. So when we call this function, we do getMAE, that first number we put here is going to go right here and set the maximum number of leaf nodes for us. Afterwards, it's going to train the model, or it's going to fit the model using the training X and training Y data. So now our model is fully trained and functional. Then it's going to do a predict, and it's going to predict using the validation X data. So again, houses that the model has never seen before. It's going to store all the sale prices for all these houses in the preds val variable. And again, these names of these variables, we could have chosen anything we wanted. These are just, nice and descriptive names, preds val. And then it's going to come down here and calculate the mean absolute error. And it's going to do that by comparing the validation Y, the actual Ys, with the predicted values. It's going to subtract those, absolute value, take the average of all of those, give us one number at the end, and it's going to return MAE. So wherever we call this function, after this function runs, it's going to replace the call with that dollar amount of how far we're off on average. Okay, so I'm going to run this bubble. Nothing will happen. It's just setting up the fact that there's a function in the background so we can use it later. Okay, now here's what we're going to do. We could run this with just this function and type in a new number of leaf nodes here, but we're going to actually, because we're computer scientists, we're going to actually create a for loop that automatically tests all of these different ones for us. Now in JavaScript, we would create something like for var I equals 0, I less than or equal to candidate leaf nodes dot length I plus plus, and that would loop us through as many times as there are things. And then inside the loop, the first thing we would do is we'd create a variable like called nodes, and we would say candidate leaf nodes I, go put that in there. So we would save this first thing in there. Well, the for loops in Python are way easier. Check this out. You type in for, no parentheses or anything, and you create a new variable. Call it whatever you want. I'm going to call this one nodes. And then in, and then we just tell it what list we're talking about. And we put that right there, and we do colon. Now watch how cool this is. For nodes, Python knows there's a new variable coming up, so it should have a name that's distinct from anything else, in candidate max leaf nodes. Once it sees that this is a list, what Python's going to do is say, okay, for the first thing in that list, the first time through the for loop, I'm going to save this first value into the variable called nodes. Next time through the list, it knows to keep going over to the next thing and store this value in nodes. And third time through, this one, this one, this one. And it knows to keep going the entire list without having to do any effort on our part. Pretty cool. Then at the end of this for statement, we need to put in a colon. This is one of the few times that punctuation is required in Python. And when I hit enter, notice how it indents me. So if the text, the code is indented, it's inside the for loop. As soon as you're ready to leave the for loop, you just kick back out to the same level as the for loop. All right, so what do we need to do? For each of these, we need to run this get MAE function so we can calculate, we can do all of this work in one line of code. All right, so I'm going to copy and paste this get MAE. And I'm going to put it right down here. And except this max leaf nodes, we've actually just called this nodes. So this is going to go right here. So the first time through, 5 is going in nodes, which means it's going to go to here as well. We're going to send a 5 in. All right, once this code runs, it's going to return the mean absolute error, a single number. So we need to put that somewhere. So let's put it in a variable called MAE, and I just did all caps on that MAE. So it runs the get MAE. It creates the model, it trains the model, it predicts the model, then it calculates the MAE, and then it returns that to us. That number is going to go right here and get pushed right into there. And then let's print that on the screen. So I'm going to do a print command. Again, make sure that you're indented. If you're all the way over at the side, that means you're outside the for loop. We don't want that. We're going to print, let's just print some words first. So the MAE for blank note. So we're going to put in, go outside the quotation marks, put in a comma. When you concatenate in Python, instead of using a plus like in JavaScript, you use a comma. And then we're going to put in this nodes thing here. So whatever the current value in the variable called nodes will go here. And then afterwards, we'll put in some more quotation marks and we'll say the MAE for 5. Okay, the word nodes comes next, but needs a space before it. Is, and then $, another comma here because we're going to concatenate in the actual MAE. So MAE. And this should print the name MAE for 5 nodes is $blank, right? All right. So let's run this and see what happens. Hey, success. One thing I do notice is it gave us a lot of decimal points on that $sign. We probably don't care about those decimal points. I bet there's a round function. There almost always is. I'm going to do round and then close MAE. One more closing parenthesis there for the print. And then let's run it again and see if it rounds the numbers. Yep, sure enough, it works just great. So it rounded it to the whole dollar. So MAE, a little weird, there's a space there, but we can live with it. So for 5 nodes, the MAE is $35,000 off. I'm actually really surprised by that. Like I would expect it to be way worse. If there were only 5 possible categories, I would expect way worse than that. Let's actually try something. Let's put a 1 up here and go with the least number of categories to see what happens. Ooh, we got some errors. Oh, yeah, that's stupid. Sure. So my guess is that of course you can't have 1. A decision tree, the first branch has 2 things, so you need at least 2 leaves. So let's run 2 leaves and see what happens. Oh yeah, look at that, 44,000. Still, I would expect it to be off by a lot more than that. That's crazy. Okay. Let's see, so that's that. And now what we can do is we can look on here and see what our best or least amount error is. And that's going to happen, let's see, 27,400, 27,200, 27,800, somewhere between 50 and 150. You might say, hey, 100 nodes is the best one, but really all that is just better than 50 and 250. The right number might be 98 or 125 or 215. We don't know where that bottom is. So to find it, we need to do some more work. Now, I think for the answer that it wants right here, the answer is technically going to be 100. What I want you to do now is I want you to adjust these numbers and see if you can figure out where the actual bottom is of this data. So what I would do here is I would know that it's between 50 and 250. So I might change this and start this at like maybe 75. Or maybe just 50. I don't know. You'll figure it out. So I know 50, so maybe start at 60 and then go 70, 80, 90, go do a bunch of them and then run those and see if you can't find the bottom. So 60, 70, 80, 90, 100, 110, 120, 130, 140, 150. It doesn't matter. We can have as many of these we want because our code will adjust and just keep running until the list is totally consumed, and maybe 180. We should really go up to like 240, but we'll see. If it's still going down over here, we'll know to go farther to the right. So we'll just bracket in some stuff and see what happens. And now we can look at this. We can just start finding, hey, where does it go down? Where does it go up at? And I'll let you kind of take care of that. Keep drilling in until you find the actual number of leaf nodes that will give us the best possible data. Okay. Now, after we're done with getting the best possible number, we need to use all the data to train our model with. So here, we've got this line of code, decision tree regressor. We're going to come up here and set the first number is going to be the max leaf nodes, and then random state 0. So I'm going to actually grab these settings so I can have them in there really easily. I'm going to pop them in here. And in all of this, I'm going to change with the max leaf nodes. I'm just going to guess, let's say it's, I don't know, 125. I'm going to guess that 125 was better than 100. And then we're going to fit final model.fit, and we're going to fit it with the full X, shift capital X, and we're going to fit it now with the full Y data. Now the reason we do this is the more data we use for fitting the model, the better the model will be, typically, almost always. So before we broke our data into training data and validation data, then we trained it and we tested it. We sacrifice some data in our training model, which makes our model not quite as good, because it's really, really important to be able to see if it's working well. Then we're able to tweak stuff, get it working as well as possible, and now we go back and we redo the model using all the data, which should make our model a little bit better. We won't be able to test that because we don't have any validation data to test that with, but we know that it gets better with more data. And then we're going to run this bubble and see how we did. Oh, I need this parameter, this first part of the parameter. Oops. This tells it that this number 125 is the max leaf node. So it's not just the first number, it needs this lead part, max leaf nodes equals 125, so they know what that 125 means. That's my bad, I apologize. Oh, so I didn't set it to the right value, so it's gonna yell at me until I change it to 100. On yours, you could do whatever you want, but the real number isn't going to be 100, I would think. It's going to be some other number. Just ignore the fact that it's going to tell you it's wrong. But if you set it to 100, it'll tell you it's right for some reason. All right, that's it, my friends. Thank you for your time and energy. I appreciate it.